This is going to be over section 23.9. We're going to be looking at dispersion. The variation of index of refraction with wavelength lambda is called dispersion. Usually n increases with decreasing wavelength. Another way to look at it is n increases with increasing frequency. Thus, the refraction is greater for light of shorter wavelength or higher frequency in a given material than the longer wavelengths. And that's kind of what you're seeing here with the red up here at the top and the blue down there at the bottom. So when white light is incident on a prism, dispersion causes light with differing wavelengths and therefore different colors to be refracted at different angles. So the dependence of wave speed and index of refraction on wavelength is called dispersion. And again, this comes, let's start back at the beginning. A white light is a superposition of waves with wavelengths extending throughout the visible spectrum. In other words, it's a mix, it's grab bag. The speed of light in vacuum is the same for all wavelengths. So they're all moving at the same speed. But once you take away the vacuum and put it in a material, the speed is different for the different wavelengths. Therefore, the index of refraction of a material depends on the wavelength. The dependence of wave speed and index of refraction on wavelength is called dispersion. And this figure shows the variation of index of refraction with wavelength for some common optical materials. The value of n usually decreases with increasing wavelength and thus increases with increasing frequency. So the light of longer wavelengths usually has a greater speed in a given material than light of shorter wavelengths. In other words, if your wavelength is longer, then you're going to see less bending of it. And you can see all of these wavelengths here. So you've got a picture here where the light is coming through white light. It starts to hit it here, and you're looking at the measure of the dispersion. How you can see the deviation here. You're also looking at how spread out the beams are over here. So the change in direction or the deviation produced by the prism is going to increase with the increasing index of refraction and frequency with with decreasing wavelength. Violet light is deviated most and red least, and other colors show intermediate deviations. So when it comes out of the prism, the light is spread out into a fan-shaped beam, just like a Pink Floyd album. The light is said to be dispersed into a spectrum. The amount of dispersion depends on the difference between the refractive indices for the violet light and for red light. So we can see in the picture above, for a substance such as fluorite, whose refractive index for yellow light is small, the difference between the indices for red and violet is also small. For silicon flint glass, both the index for yellow light and the difference between the extreme indices are greater. So the brilliance of diamond is due in part to its large dispersion and in part to its unusually large refractive index. Crystals of rhyolite and of strontium titanate, which can be produced synthetically, have about 8 times the dispersion of a diamond. So when you look at a rainbow, you're seeing the combined effects of dispersion and of internal reflection. The light comes from behind you and is refracted into many small water droplets in the air. Each ray undergoes internal reflection from the back surface of the droplet and is reflected back to you. The dispersion causes different colors to be refracted preferentially at different angles. So you can see the various colors as coming in from different regions of the sky, from forming concentric circular arcs. When you see a second slightly larger rainbow with its colors reversed, you are seeing the results of dispersion and 2 internal reflections. So you can see the primary rainbow, you can see the secondary rainbow, but if you watch, look at the colors. Colors are inverted as to what they are, and that's what it's talking about here. You're seeing the results of dispersion and 2 internal reflections. And here's sort of a picture of what's going on. You've got the rays of sunlight that form the primary rainbow and refract into the droplets, undergoing internal reflection and refract out. So you've got angles exaggerated for clarity, obviously. You're looking at about 40 degrees. So you've got incident white light coming in. Your level of perception here is going to be around 40 to 42 degrees. So you've got them coming into the drops, and then they're coming back to the eye. So the two refractions are going to disperse the colors. You've got ones that bounce here and then bounce out and then come back to the eye. And that's what you're seeing here. You've got some that are going to go straight through, and then you've got some that bounce around and then come back at you. So that secondary rainbow is formed by rays that undergo two refractions and two internal reflections. And the angle is, of course, going to be greater for violet than it is for red. And that change about there is part of the reason why you're seeing the change here from the order of the colors.